There, my name is Sam Monkman, and today we're going to be talking about null spaces. Null spaces are a super cool part of linear algebra, and are actually a specific version of another cool aspect of abstract algebra, which is called a kernel. So basically, a kernel is just all the stuff that gets sent to zero by any type of transformation, and a null space is the specific version of that for vector spaces. So a null space is all the stuff that, for any matrix A, doesn't matter what the matrix looks like, doesn't have to be square. For any matrix A, a vector is in its null space if that multiplication by our A sends that vector to 0. So that's all I really need. I just need to go to 0. And we're going to be trying to see if this name, null space, actually makes sense. We're going to try to prove that the null space is, in fact, a vector space. So let's just quickly start off by stating that A is a matrix. And that N is its null space. So every vector in N multiplies by A to get 0. And this is all going to be for right multiplication of the vector, just to be clear. So let's quickly show that the 0 vector is where we want it to be. We'll start off with that. 0 vector. And I'm going to use that arrow notation for the 0 vector. I'm not going to do it for most of my vectors because it's pretty clear when we're talking about a vector. We just want to specify that that's not a scalar. Okay. So 0 vector. Now, I'm going to, what do I want? I want 0 vector to be in N. In other words, I want A times the 0 vector to equal the 0 vector. But wait a minute. Do we remember this guy? For all matrices M, the 0 vector times M is the 0 vector. It's as easy as that. I'm done. Great. Moving on. Let's look at the slightly harder part, the scalar multiplication. So we're going to consider some constant and some vector already in N. And remember, we just need closure and some v in N. Remember, we just need closure under scalar multiplication. So I want to show that this is true. I want for A times CV, which is my new vector, to be equal to the 0 vector. I want it to be in that null space. So we may remember this guy. A times CV is equal to C times A times V, right? Because we all know that matrix multiplication associates, but it only commutes for scalars, but C is a scalar, so it works out. So this scalar C, I don't know if you guys can see this through the screen, that scalar C commutes, so I have CAV. Now, because I can associate, I group these fellas up together. I have CAV, and wait a minute. Oh, I can also actually associate it like this. Look at that. All right. So now I have C times, but wait, AV is 0 because V is in the null space. And a constant times the 0 vector is the 0 vector. Perfect. All right, we have one thing left to show. Vector addition. This is the fun part. So we're going to consider two guys in the null space. Consider V and U in the null space. So A times V is equal to A times U, and that equals the 0 vector. Now I want to show that when I add those guys together, it also goes into that null space. So I want A times V plus U to be the 0 vector. Now, what you may remember from a little earlier on in linear algebra is that this matrix multiplication actually does distribute over vector addition. A times v plus u is equal to AV plus AU. But wait a minute. What do we know about these two guys? That's right. AV equals 0, which is the same as AU. So A times V plus U is equal to is equal to 0 plus 0. Quite famously, 0. QED, and we know that the null space is in fact a vector space. Thank you very much, and I will see you in the fall.